Hello everyone, and welcome to this session on Cisco CCNA routing and switching. Today, we are going to break down the absolute fundamentals of network communication by diving into IP4 addressing. Whether you are studying for your CCNA exam or just entering the networking field, understanding how IP addresses work is your most essential building block. Let's get started. Before we jump into the numbers, let's look at our roadmap for today. We will start by exploring the mathematical number systems used in networking. Next, we will analyze the structure of an IPv4 address and how it is divided into network and host portions. Finally, we will cover prefix lengths, subnet masks, and the legacy address classes that laid the foundation for modern subnetting. To master networking, you need to understand three core number systems. First is decimal, or base 10. This is how humans read addresses, using digits 0 through 9. Second is binary, or base 2. This is how routers and switches process addresses behind the scenes, using simple on-off states represented by zeros and ones. Lastly, we have hexadecimal, or base 16. Hex uses digits 0 through 9 and letters A through F. It is used heavily in IPv6 and MAC addresses to represent long binary strings in shorter, more concise chunks. Let's look at how these systems calculate value mathematically. In our everyday decimal system, each position represents a power of 10. For example, the number 1526 is calculated by adding up 1 times 10 to the power of 3, plus 5 times 10 squared, plus 2 times 10 to the power of 1, plus 6 times 10 to the power of 0, equals 1000, plus 500, plus 20, plus 6, which equals 1526. In binary, positions represent powers of 2. The binary number 1011 translates to 1 times 2 to the power of 3 plus 0 times 2 squared plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0 equals 8 plus 2 plus 1, which gives us 11 in decimal. In hexadecimal, we have 16 numbers, and we count from 0 to 9 just like normal. But when we hit 10, we use letters instead. So A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. For hexadecimal system, each position represents a power of 16. For example, the hex value 1A translates to 1 times 16 to the power of 1 plus 10 times 16 to the power of 0 equals 16 plus 10, which gives us 26 in decimal. Now let's apply this to an actual IPv4 address. At layer 3 of the OSI model, an IPv4 address is a 32-bit logical identifier assigned to a network interface. This 32-bit length is divided into exactly 4 8-bit sections called octets. For human convenience, we write it in dotted decimal form, like 192.168.1.240. But your computer and router read that exact address as a long string of 32 binary bits grouped into 4 distinct octets. Let's see exactly how that 32-bit binary string translates back into 192.168.1.240. For the first octet, 11 followed by 6 zeros combines the place values of 128 and 64 to equal 192. The second octet turns on the 128, 32, and 8 bits to give us 168. The third octet only has the very last bit turned on, which equals 1. Finally, the fourth octet turns on the first 4 bits, 128, 64, 32, and 16, which sum up exactly to 240. To do this quickly, you need to memorize the binary values of an octet. Remember, an octet is just 8 bits. And because of this math, each decimal number in an IP address will always range from 0 to 255, from left to right. The positional values double every time, giving us the standard networking matrix 128, 64, 32, 16, 8, 4, 2, and 1. We use these exact position numbers to convert back and forth between binary and decimal. Converting from binary to decimal is a simple 3-step process. Step 1, write out your place values. Step 2, multiply the bits by those values. Step 3, add the results together. Look at this example. For the binary string 10101010, we simply add the active place values 128, 32, 8, and 2 to get a final decimal value of 170. Let's practice with 2 more examples to lock this in. In example 2, the active bits are at the 128, 16, 8, and 1 positions. Adding those up gives us 153. In example 3, every single bit is turned on except for the very last one. Summing 128 all the way down to 2 gives us 254. If that last bit were turned on as well, it would reach the absolute maximum value of 255. Now, how do we go backwards from decimal to binary? We use a subtraction comparison test. You ask yourself, is your decimal number greater than or equal to the bit value? If yes, write a 1, subtract that bit value, and move to the next position. If no, write a 0, keep your number, and move on. Let's try 165. 165 is greater than 128, so we write a 1 and are left with 37. 37 is smaller than 64, so we write a 0. Then 37 is larger than 32, so we write a 1, leaving us with 5. We place zeros at 16 and 8, a 1 at the 4-bit position, a 0 at the 2-bit position, and a final 1 at the 1-bit position. 165 in binary is 1, 0, 1, 0, 0, 1, 0, 1. Let's run through one more conversion using the number 200. 200 is greater than or equal to 128, so we write a 1 and subtract it, leaving 72. 72 is greater than 64, so we write another 1, leaving us with 8. Since 8 is smaller than 32 and 16, we write zeros for those slots. However, 8 is exactly equal to our next bit value of 8, so we write a 1. With our remainder now at 0, the remaining slots for 4, 2, and 1 all become zeros. This gives us a final binary value of 110010000. An IP address isn't just a random string of numbers. It is always split into two functional halves. Part 1 is the network portion, which identifies the specific local network or subnet the device belongs to. All devices on the same local network must share this exact same portion to communicate directly. Part 2 is the host portion, which uniquely identifies the specific device, like a PC, phone, or router interface within that network. Every host on the same network must have a unique host portion to avoid IP conflicts. So, how do devices know where the network portion ends and the host portion begins? They look at the prefix length, also known as the CIDR notation. For example, take the address 192.168.1.101 with a /24. Out of the 32 total bits in the address, the /24 tells us that the first 24 bits are firmly locked for the network portion. The remaining 8 bits are left wide open for assigning unique host addresses. Let's focus deeply on this table. The prefix length and the subnet mask are two ways of saying the exact same thing. The subnet mask tells the router exactly where the network portion ends. In binary, a mask uses continuous ones to mask out network bits, and continuous zeros for host bits. Look at a /8 prefix. It means the first 8 bits are binary ones, which translates to a decimal mask of 255.0.0.0. This leaves 8 bits for the network and 24 bits for host deployment, allowing for millions of unique addresses. As you move down to /16 and /24, more network bits are locked down. A/24 turns on 3 entire octets, giving us 255.255.255.0. This leaves exactly 24 bits for networks and 8 bits for hosts. When we look at a classless prefix like /28, we cross into the final octet. It locks 28 network bits, leaving only 4 bits for host devices. In decimal, adding those 4 binary placeholders gives us a mask of 255.255.255.240. Remember this rule? A longer prefix secures more networks, but leaves fewer addresses for host devices. Let's walk through a practical example to see how a router calculates the exact network portion using binary logic. In this first example, we have a device with the IP address 192.168.1.100 and a standard /24 prefix. As we learned, a 24 prefix means that the first 24 bits of the mask are continuous binary ones, and the remaining 8 bits are binary zeros. This translates directly to a decimal subnet mask of 255.255.255.0. Now look at the calculation below. When your router processes traffic, it performs a logical AND operation, comparing the IP address bits straight down against the subnet mask bits. Wherever the subnet mask has a binary one, the IP address bit is preserved and locked down for the network portion. Wherever the mask has a binary 0, the host bits are completely wiped out and reset to 0. Because our mask's ones completely fill up the first 3 octets, the numbers 192, 168, and 1 remain completely unchanged. The final 8 zeros clear out the last octet entirely, turning 011001000 into 8 zeros. This tells the router that this host belongs to the 192.168.1.0 network. Now let's look at example 2, where we step into classless subnetting by changing the prefix length to a /26. This time, our target IP address is 192.168.1.155. A 26 prefix means we have 26 continuous binary ones. This fills up the first 3 octets with 24 ones, and then borrows 2 extra bits from the very beginning of the 4th octet. In decimal, adding those 2 active place values, 128 and 64, gives us a custom subnet mask of 255.255.255.192. Let's look closely at the math for that critical 4th octet. The decimal host number 155 is written in binary as 10011011. When we drop the mask down to run our calculation, look at what happens to those first 2 bits. Because the mask has 1s in those 2 slots, they are preserved. The remaining 6 bits hit the mask's zeros and are immediately wiped clean. As a result, the final octet changes from 155 down to 100000 in binary. That single remaining bit sits in the 128 placeholder value. By adding our 4 calculated octets back together, the router determines that this specific device belongs to the 192.168.1.128 network. Historically, before classless routing existed, the Internet was strictly divided into 5 distinct classes: A, B, C, D, and E. A router would look at the very first octet of an IP address to instantly determine its class and default mask. Class A addresses always start with a value between 0 and 127 in the first octet. They were designed for massive organizations because their default mask is 8, leaving a giant pool of over 16 million hosts per network. Class B addresses range from 128 to 191 in the first octet. Their default mask is a 16 that is 255.255.0.0, which perfectly splits the address in half, 16 bits for the network and 16 bits for hosts. Class C addresses range from 192 to 223. These have a default mask of 24, making them ideal for small businesses or local networks because they only allow up to 254 usable hosts per net. Now, what about the rest of the numbers? The ranges don't stop at 223. This brings us to Class D and Class E, which function very differently because they do not use default subnet masks and cannot be assigned to normal host devices. Class D spans from 224 to 239 in the first octet. This entire block is strictly reserved for multicast traffic. Finally, Class E spans from 240 all the way to the absolute limit of 255. This block is completely closed off and reserved for experimental and research purposes. That concludes our core look at the basic structure and math behind IPv4 addressing. In our next session, we will take these concepts further and learn how to actually subnet a network from scratch. Thank you for watching, and happy networking!